Okay, let's just get started. Let me just quickly introduce myself. I'm Dr. Abidul Freak, founder, chip expert, and chip academy. I've been training a lot of people in the design verification area for a while. So let's just get started. So before we just dive into the whole space of design verification, let's just see the bigger picture first. So let's say we want to design ASIC, and what are the steps involved. So typically you get the requirements specification from your internal product team or from your customers. So this is your step one. And let's say someone asks you to design a RISC-V processor based SoC with a crypto module, and so there will be a detailed specification as to what kind of a RISC-V processor it will be, like the pipeline strategies, the ISA support, the peripherals that is required in the SoC, and so this kind of specifications are very clearly mentioned, along with the specification, like in terms of what will be the frequency that is required, what should be the power and area. So these requirement specifications are then actually taken up by the microarchitecture team, and they design microarchitecture, spending months of efforts, and at the end they get an RTL, which is typically a SystemVerilog code or a Verilog or a VHDL code, and then this RTL is then handed over to the design verification team, which then performs verification at multiple hierarchy, like starting with the let's say unit level verification to the code level verification for different peripherals, and then the chip level verification combining the processor and the peripherals. So at the end it's like we get a verified RTL. So you can see, so typically you have typically you have 2-to-1 ratio of verification engineers compared to your design engineers, and you can see that 70% of your code base is actually in verification. So you spend a lot of time in verifying the thing, because unlike software where you can just send a patch afterwards to fix the thing, in hardware you don't have that kind of luxury. So you really spend a lot of time in verifying things. Once you have the verified RTL, then you can give it to the physical design team. So we take this RTL and run it through that RTL to GDS flow, like the design library setup, floor planning, placement and routing, timing closure, and finally we have this whole sign off and get a GDS2, which is then sent to the fab for fabrication, and also the pin info also take it out from here to give it to the PCB design team. So these two things are being done in parallel, this fabrication and PCB design. And this PCB design team also get this requirement from the requirement specifications as well, what kind of interfaces are required. And then so this after the fab gives you the die, you give it to the packaging company will just package it for you and get a chip, and you have the PCB ready, you have a chip, you just stuff it out. So this is 7, I would say. So this is 8 step, and then once the chip has been stuffed on the PCB, then you bring it out, do some preliminary test on it just to make sure that all the interfaces are working, your SPI, and so this is the whole complete flow. Okay, so let's just move ahead and see a bit more detail about the requirements. So the design verification team not only gets the RTL as input, but also get the requirement specifications, and I will let you know shortly that why these requirement specifications are required. And like with the physical design team, also get the specification in terms of the PPA, power, performance, and area requirements. But in this course we just focus on the design verification part. So let's just see why these requirement specifications are reside in the design verification stage. Okay, so let's see that you get a requirements and you build an RTL and then you hand it over to the design verification team to test it. If you just get the RTL from the RTL designers and we test them for different cases, so basically what we are doing here is we are testing, we are verifying what has been built by RTL engineers. Okay, so the problem with this thing is that we are not verifying what is required by the requirements. Okay, we are just verifying what has been built. Okay, so verification is not to test what is built. Instead, verification is to test what was supposed to be built. Okay, so therefore what is supposed to be built was provided by the requirements. So this requirement specification document is the first input. So it is given to the RTL people and as well as the design verification team. I should take this requirement specification and start preparing the verification environment, what are the test cases that needs to be tested without waiting for the RTL. Okay, so verification is to test what was supposed to be built. Okay, so therefore understanding the requirements of the chip is extremely critical. Okay, so RTL engineer doesn't have to spend a lot of time in understanding the requirements, and so just to make sure that it is verifying what was supposed to be built. Okay, so how does we get the verifications? Actually, let me just give you a very simple example, and this will be we will be using it in our labs and a lot in the lectures as well, so just to get understanding. So let's say we have requirements to design a single port memory, and the requirements specifications are in terms of like what is the what will be the depth of the memory. So in this case we have an address lines of 5 bits, so it is 32 deep, and data is 8 bits, so each location is 8 bit wide. Okay, and then we can have synchronous read and write operation, and since it's a single port, so we cannot read and write be high simultaneously. So this is a constraint on here, and typically you will be getting the timing diagram as well. So let's say this memory write cycle, so you have address and data in, and this is the write signal when it is high, and read has to be low, and then this you can see here in this clock typically you're writing, the write signal is high, and then whatever data is there, it is written at this address. Okay, so for this second clock cycle, so we have write here, and then second clock cycle we can see that this is low, so there is no write, and then we have again high here, so write and write. So you need to understand the timing diagram of write cycle. Likewise we have the read as well, so you can see here write is low, read is high, and you will be getting, you will put in the address and you will be getting the data. And likewise here we don't have a no read because it's, and then we have subsequently read as well. Okay, so now in order to design this memory and then test it, typically what you do is, and you have been doing it in your alternate design classes, that you actually design it in SystemVerilog or Verilog, where you, for a memory, you specify the ports, input, clock, read, write, and then address and data, and then you have a sequential block, always positive clock, and then you check if there is write is high and read is equal to 0, because it's a single port memory. So write, so memory address is equal to data, so whatever address is there, so you just write it, the data at that memory address, and then let's say if write is equal to 0 and read is equal to 1, then you get the data at that particular address. So this is your design. And then you have a test bench as well, where you just actually make an instance of this one here, and then you describe the signals over here for all these clock, read, write, and then basically you set up your driver part. So you generate a clock, so clock generation, and then you actually set up your stimulus to have a write operation at positive clock. So write is equal to 1, read is equal to 0, and then put the address and data they want to write. So this is how you actually test your memory, and you have been doing this for a while. So then the question is, why design verification as a separate profession when RTL engineers can test their design through test benches? So we need to address this, and we have 10 good reasons to talk about. So why design verification is really required. So we are going to stop this video at here, and in the next video I will be discussing about the 10 reasons why design verification is really required. Thank you.